Hello and welcome to this new video. So this is the third appendix, Appendix C to Chapter 1, how to compute square roots. Okay, it's an important question actually because in school you learned how to do addition, multiplications, divisions, and so on. But how to compute radicals? Okay. I'm going to explain a simple algorithm for doing that. So let us start, and we know actually, the idea is that we know that every real number is the limit of a sequence of rational numbers, okay? And rational numbers are obtained from addition, multiplication, divisions of integers, right? So we use this, but what I'm going to explain now is that I will find a computable sequence of rational numbers converging to radical 2. Okay, we know that it exists, but I'm going to exhibit an explicit sequence. Okay, so let us start with the radical 2. Okay, there are many methods actually of computing, but I will explain one of them, the simplest one. Okay, you start with an initial guess of radical 2. Okay, so for simplicity, just can start with x0 equal to. You can start with 1 actually. And now we define a sequence by induction with the following way. So xn plus 1 is 1/2 of xn plus 2 over xn, or 1/2 xn plus 1 over xn. Okay? So if we know x0, we know x1. If we know x1, we know x2, and so on. So this is perfectly correct. But of course, we have to make sure that xn never vanishes, which is what we shall prove actually. So and if it's well defined, then it should be a sequence of rational numbers, because if x0 is rational, x1 would be rational. If x1 is rational, x2 will be rational, and so on. So now I'm going to prove rigorously that this sequence is well defined and converges to radical 2, and it's decreasing actually. So it's an approximation of radical 2 from above. Okay. So first thing, but before doing that, let me just compute for you the first 3 terms, just to understand what's happening. So x1, if you replace x, so take n equals 0 in this equation, you get x1 equal 1/2 x0 plus 1 over x0. But I took x, for simplicity, x0 equal 2, so you got 1/2 of times 2 plus 1 over 2, so it's 3/2. Okay. Now the next term, you take n equal 1 here, so you get x2 equal 1/2 of x1 plus 1 over x1. So just replace. So you get, if you do the algebra, you get 17 over 12, which is about 1414666. And the third term is 1/2 of the previous term plus the inverse of the previous term. So if you do the computation, you will get 17 squared plus 12 times 24, so you get that. And it's approximately 1.41415. So we already see numerically that we are converging to radical 2, because we know what is radical 2. Okay, now I'm going to prove that xn is well defined actually. It's decreasing, it's bigger than radical 2. Okay, so step by step. First, xn is bigger than radical 2. By induction, for n equals 0, it's true because I took x0 equal 2, and 2 is bigger than radical 2. Even if I don't know what is radical 2, this is true because 2 squared is 4 and radical 2 squared is 2, so 4 is bigger than 2, so it's true. Okay, so it's true for 0. Suppose it's true for some n. Just compute xn plus 1 squared minus 2 and prove that it's positive. So if you replace xn plus 1 by its value, you get that, and you complete the squares, you get you expand the square actually, so you get xn squared over 4 plus 1 over xn squared plus 1 minus 2. So this is minus 1 here. And if you reduce to the same denominator, you will get xn4 plus 4 minus 4 xn squared over 4 xn squared. And now we observe that this is a perfect square. So this is just xn squared minus 2 squared over 4xn. And this is something strictly positive, actually, because my assumption, okay, so that's it. So by induction, xn, taking the roots, actually, xn will be bigger than radical 2. Okay, to prove that xn is decreasing, it's enough to prove that xn plus 1 is less than xn. And you just compute the difference. Okay, so replace xn by its value, xn plus 1 by its value, and if you subtract xn, so you get minus xn over 2 plus 1 over xn, and if you reduce to the same denominator, you get 2 minus xn squared over 2xn, and this is something strictly negative. Okay, so I proved that xn is well defined, decreasing, bigger than radical 2. So in particular, it's bounded from below, and you know that every decreasing sequence which is bounded from below has a limit, is convergent. So I know that xn converges to some limit, and by this inequality, the limit will be bigger or equal than radical 2. Now I will prove that actually the limit is exactly equal to radical 2, and this is not difficult. So in particular, this inequality tells me that x is positive. Okay, consider the recurrence relation linking xn plus 1 to xn, and let n tend to infinity. Then the first term converges to 1/2 x, the second term to 1 over x. And if xn converges to x, then xn plus 1 also converges to x. So at the limit, I get x equal 1/2 x plus 1 over x. So 1/2 x is 1 over x, and therefore x squared equal 2. So either x is radical 2 or x minus radical 2, but the second possibility cannot hold because x is positive, actually, because it's bigger or equal than radical 2. So therefore, I know now that, so I defined a computable sequence of rational numbers converging from above to radical 2. Okay, so I can use this to approximate radical 2. Now, so I get an algorithm for computing radical 2 to some degree of accuracy. But the question is, when should I stop this iteration? To which index I should stop? For n equal 10, 14, 100? Well, to answer this question, we have to do what we call error estimates. So let us estimate xn squared minus 2. Okay, it will follow the so an estimate for xn minus radical 2 will follow, actually, as we shall see. So we already established this relation, xn plus 1 squared minus 2. We already established that, and now I know that xn is bigger than radical 2. So xn squared is bigger than 2, so 4xn squared is bigger than 8. So the 1 over 4xn squared is less than 1 over 8. Therefore, I get this inequality, which is an error estimate, actually. So xn plus 1 squared minus 2 is less than 1 over 8 times the previous error to the square. So this is what we call a quadratic. The error is quadratic. So at each step, the error is raised to the power 2. So it means that the accuracy is multiplied by 2, actually, if you like, or squared, if you like. Okay, so in particular now, if you take n equals 0, then we get x1 squared minus 2 is less than 1/2. Okay, because this is x0 is 2, so x0 squared is 4, so 4 minus 2 is 2, so 2 squared is 4, so 4 over 8 is 1/2. Okay, and now take n equal 1. So we get x2 squared minus 2 less than 1 over 8 times the previous error squared. So it's less than 1 over 8 times 1/2 squared. And this is just 1 over 2 to the 5, or 1 over 32. But I can write this as 2 to the power 3 over 2 to the power 8. You will see why I wrote this in because I need a pattern now. Okay. Let us do one more step. Apply this inequality to n equal 2. So we get x3 minus 2 is less than 1 over 8 times the previous error to the square. Okay, but the previous error was less than 1 over 2/5. So when I raise to the power 2, I get 1 over 2/5 squared. So it's 1 over 210, which is actually 1 over 2 to the 13. And I can write this as 2 to the 3 over 2 to the 16. So now I hope that you saw a pattern that you can prove by induction, that this power here actually is 2 to the n plus 1. Okay, so it's 2 to the 2 to the n plus 1. Okay. So of course we verified this for n equals 0, 1, 2, 3, 1, 2. So you can use induction to prove that. Now, but I need to estimate xn minus radical 2, but this follows from this actually, because I can factor xn squared minus 2 as xn minus radical 2 times xn plus radical 2. And now I know that xn is bigger than radical 2. So this term is bigger than 2 radical 2, which is just bigger than 2 actually, because radical 2 is bigger than 1, even if I don't know what is radical 2. So I get that this quantity is bigger than 2 times the error. This is the error actually, and I can put absolute value here because this is something positive. Okay, so I get what? I get 2 times xn minus radical 2 less than 2, 3 over 2 to the 2 to the n plus 1. So when I divide by 2, actually, I get 2 squared here. So the error, the absolute error, is less than 2 to the 2 over 2 to the 2 to the n plus 1. And I can rearrange that. I can write this in several ways, actually, if I do the math. So it's just, I can write 2 to the, so in power, here I get 2 to the n plus 1 minus 2, which is just, I can factor by 2, actually. So the power of 2 is 2 times 2n minus 1. So, and I can write that as 1 over 4 to the power 2n minus 1. Okay, so the power is 2n minus 1. Right? Fine. So, for example, if you take n equal 4, what is this? So, what is this? What happens to this quantity? This is just, so if n equal 4, 2 to the n is 16. So I get 4 to the power 15 or 2 to the power 32. But 2 to the power 32 is about 2 billion, right? So I have 1 over 2 billion. So it's less than 1 over 1 billion, 10 minus 9. Okay? It's easy to see that. So what does this mean? It means that if n is equal to 4, this quantity is less than 10 to the power minus 9. So the error is less than 10 to the power minus 9. So, and what does it mean? It means that the 9 decimal places of x4 are correct. Okay, so if you like, the first 9 decimal of xn coincide with the first 9 decimals of radical 2. So I know that x4 is an approximation of radical 2 with an accuracy of 10 to the power minus 9. This is the epsilon, if you like, that we talked about. Okay, if you take n equal 5, we get something better. We get 1 over, the error is less than 1 over 2 to the 62, which is actually, so 2 to the 62 is actually 2 billions times 2 billions. So it's 4 billion, okay? So it's less, so billion is 10 to the power minus 9 times itself. So I know this, I know that the 1 over 262 is less than 10 to the power minus 18. So in principle, if all operations are done correctly with an infinite precision, which is not the case always actually, I know that x5 is an approximation of radical 2 up to 18 decimal places. Okay, but in practice, when we do the computations, first of all, any computer actually has a fixed degree of decimals, so you cannot have an infinite accuracy actually. So there are errors that are accumulated at each step, at each computation that we do. We lose precision. So in theory, actually, X5 should be an excellent approximation of radical 2. Okay, now I will implement this actually shortly in Python and see what happens in practice, actually. So, but in principle, X5 is an approximation of radical 2 up to 18 decimal places. Okay. So we proved actually that the convergence is very, very, very fast. Okay, so 4 or 5 iterations are already we are there. Okay, so but I need to tell you something. We started with x0 equal 2. If you started with x0 equal 1, okay, you will convince yourself that x1 will be bigger than radical 2 actually. So and the sequence starts decreasing from n equal 1 and not from n equal 0. So the first term, you should pay attention to the first term actually. You can start with any initial guess actually, it doesn't matter. The sequence will be convergent to radical 2, but it will be decreasing starting from n equal 1 and not from n equal 2 or from n equal 0. Okay. Okay. And more generally, using this method, actually, we can compute the radical of any positive number a by the same scheme. So instead of 2, you put a actually. If you want, you can repeat the same analysis that we did. We can prove that the sequence is decreasing from n equal 1 and it's bigger than radical a, and okay, and when you let n go to infinity, you will get an equation and you get that the limit is radical a. So it's same thing, same. Okay. Now, how did we invent these formulas? These formulas are actually a particular case of Newton's method that you will learn in numerical analysis. So Newton's method is a method to approximate the zero of, or the solution of an equation of the form f of x equals 0. And under some assumptions, actually, if we define this formula, this sequence by induction in this way, actually, we can prove that if we started sufficiently close to x0, to the real root, actually, this sequence is convergent and very rapidly. Okay. Sometimes it diverges, right? It's not the case of what we started with, actually. So in this case here, this particular case, the sequence is always convergent, and no matter what is the initial guess, actually. You can start with any guess. However, we may have some problems depending on f. Sometimes it's divergent. Okay. So 1 is a particular case of 2 when you take f of x equal x squared minus a, right? So therefore, f prime of x is 2x. So if you do the computation, you'll find that this is a particular case of this Newton's method. Okay. And last thing I want to say is that there are even still more efficient algorithms to compute square roots that computers use, actually, but we're not going to explain them because they require a deeper knowledge of computer science and the internal representation of numbers in a computer and so on. But I wanted to illustrate one method which is very efficient, actually. So just after 3 or 4 steps, you have a very good approximation of radicals. Okay, so in principle, you can do that by hand. You don't need a computer. Okay. Okay, so this concludes this video. In the next video, I'm going to implement the simple Newton's algorithm to compute radical 2. Okay, so thank you for your attention.